Right, yeah. Hello, everyone. A lot of familiar faces. I haven't actually spoken at a group like this for a while, because my job has sort of changed. I used to do a lot of this kind of, I'd learn up a technology and then come along with lots of nice little demos to show you how to do something, usually about UWP or Windows Phone or some kind of technology related in that area. I've always been interested in client application development, and actually I've always been interested in doing it on small devices. And in the old days, before mobile phones were like these amazing, hugely powerful, high capacity computers, it used to be quite challenging. So it was quite good building for Windows Mobile or something, doing all the track and scan stuff, you know, and work. You used to have to do tricks. I remember we used to have this thing where you could actually run two processes on a Windows Mobile device in two different slots, and you did this weird process-to-process communication because you needed the additional address space, because we were, you know, it was like 32 watts. I can't even remember. You see, you don't even think about these things anymore. We have no limits. We have like masses of address space, and we have masses of storage. And the one thing we don't have still, actually, is reliable network connectivity. And I always used to, I remember when Windows Phone first came out, and there were all these people standing up and talking about it as if developing for it was like developing for a PC. It's like, you know, and I'm sitting there seething going, you do realize these things run on a piece of wet string, and you're trying to do all this amazing kind of database programming over a network and all this kind of stuff. So I've always liked tough challenges. So it's kind of a natural thing for me to get into IoT and sensors, because, you know, it's still client computing. It's still where computing, the rubber hits the road. It's still where, you know, we're working directly where computing interacts with people or the things or devices. And I kind of like this kind of thing. So the long title of this talk is Sensors in Sports. Measuring and analyzing human performance with sensors, Xamarin, Azure, and ML, which is a very boring long title. But the short title is How to Go Skiing on Expenses. I've had a really interesting winter, actually, because the group I'm in, CSE, Commercial Software Engineering, a lot of the work that we do these days is actually hacking with partners or with internal teams. We kind of travel somewhere, and then we take over a venue somewhere, and we work with partners, and they've got a particular business problem, and we've got a technology that we think will solve this, and we just hack, we just build stuff. It's great fun. It's quite different from how my job used to be, where I would kind of produce an interminable 20 hours of videos or something, put them up on onto Microsoft, what was it used to call? Microsoft Channel 9, yes, yeah, and then Microsoft Virtual Academy thing, whatever it was called, I can't remember. 20 hours of videos, you know, and this is great, and it was good. I mean, a lot of people have thanked me and come up to me and said, "Oh, I learned how to program Windows Phone." But I used to be the master of the little sample app. You know, you could demonstrate how something worked, and then when people actually tried to use it in a real application, of course, it was never that simple, because sample apps never have things like error handling or anything useful like that, or we never actually have to do architectures like MVVM. So this is different. I'm now working with partners, and we're really building real stuff. And as part of that, these hacks get organized with partners, and we have this website with all of the upcoming events, and basically people are asking for collaborators. So up to a point, we can volunteer to go anywhere and work on anything that is our area of interest. And so back in towards last autumn, this collaboration request came round, and this Sensors in Sports came up, and, you know, it's for looking for developers who are interested in IoT, applying it to sports. And I'm very keen on outdoor pursuits. I love skiing, I love climbing and mountaineering, and any excuse I'll be out in the mountains. So I looked at that, I thought, oh, this sounds good. I can actually do my love of getting involved with sports and actually do my job at the same time. So this is how I got involved in this project. And it's and as a result of that, we've had a lot of hack events actually held at ski resorts over the winter. So we started off in November in Copper Mountain in Colorado with the United States ski team, and then we moved on to Austria. We were working with a major ski manufacturer in Austria, and then we were back into Washington State with the internal. We were up at Crystal Mountain, which is an hour and a half, 2 hours from Seattle, up in the Cascades, and then we were back in Austria, and then there's been a couple of other events. I haven't even been on all of them, so there's a lot of very hands-on. We're there, we're working with skiers, we're gathering data, and the project is all about, we want to bring technology to sports performance analysis. So let me ask you, can you name a sport where technology is really kind of a big deal? Where's technology really kind of making a big impact in sports? Anyone, any suggestions?
Bowls.
Not yet, but bowl. I thought about bowls. I thought, we could put one of these sensors in. No.
Yeah.
Formula One. Yeah, of course. Now that's teched up to the eyebrows. Cycling, actually, at a professional level, there's lots of, they not in competition, but in training, they swap out the crank, and they get super detailed thing about all the power cyclist is generating, and obviously all that sort of thing. Tennis, well, only through observation in terms of using technology to figure if the ball's in or out. That's the kind of Hawkeye stuff. But no, there's huge scope here for technology to be applied to sports. It's an open playing field. There's a lot, pun intended. There's a lot of stuff going on that we can really bring sensors to make a difference. So the state of things at the moment actually is there's not a lot of people really trying to. There's a few specialist companies typically selling sensors to football clubs and things like that. So there's a few ISVs out there creating solutions, but there's no standardization across anything. There's no interoperability between different solutions. So there's no real defined standards. And generally, thinking about skiing, actually, the top ski coaches, even like the United States ski team, their performance analysis is generally just by visual, watching it. They might set up a few video cameras, or obviously we've got TV feeds at the big events, so they've got cameras all the way down the course, and they're watching somebody's performance, but it's all experience, it's all visual. There's no real kind of high resolution measurement going on. So, but this is a great opportunity for machine learning. And also we've got a couple of things, as in a lot of fields, are coming together to make some interesting things possible. Hardware is getting really cheap. These are the things I'm going to be talking about mainly tonight. These little guys, they're basically Arduinos in there, run off a little watch battery. This is part of my essential toolkit, as I have a bag full of these, because you have to change them all the time. And these little things, but they're like, these guys are about, I don't know, I'll show you on the website in a bit, but they're like 40 euros or something for one of these, so cheap as chips. And they're really powerful computers with lots of 9 dimensions of measurement of different of sensors in them. So the hardware is available, it's cheap. So we can now gather huge amounts of data. So we've got the data, and as you know, data is the new oil these days. If you've got data, you've got something that you can then mine to get interesting insights. So this is a great human activity recognition is a great new application for machine learning, and it's an emerging field. So, but it's also one that's quite experimental at the minute, because a lot of up to now machine learning has been applied to predictable things like actual mechanical processes and this sort of thing. But it says on the slide, human body is not as predictable as a car, camera, or drilling machine. And if you think about something like skiing, there's so many variables. The skill of the skier, the weather conditions, how warm it is, how wet the snow is, how icy it might be, and how bumpy it all is, and this sort of thing. So there's a lot of challenges in A, getting clean data, and B, analyzing it and getting insights. So we've actually got a whole team. This project grows and shrinks, and there's loads of data scientists working on it. Have we got any ML specialists in the room? That's a relief, good. Because ML is in the title and I will be touching on it, but I'm very much on the client. I'm talking to IoT, I'm Xamarin, I'm Bluetooth, I'm sensors. I get the data and then we put it in the cloud and then magic happens up there. And there's the machine learning analysis goes on, and I'll talk a little bit more about the insights we're trying to get from this thing. So it's a real exciting field to be in. There's a lot of stuff that we can do. We've got sensors which actually gather the data, so we can instrument athletes and get data from them. And those sensors, they typically talk Bluetooth LE, and you need to talk to something. So in this kind of environment is some kind of a gateway, so an IoT gateway, if you like. It's something that's going to pull the raw data off and then do something with it. Actually, in our case, is upload it to Azure. This tends to be a mobile app in our situation. So one thing that's interesting about skiing is that we, again, coming back to that network connectivity point, we don't have reliable networks. We need to be able to, what we can do is put our phone near to these sensors and use Bluetooth LE to get the data, and use that phone app as a gateway to gather that data, amalgamate it, maybe do some processing, and then when we've got internet connectivity, which may be intermittent on a ski resort, upload it to Azure for additional processing. So this guy actually uploads the data into Azure somewhere, and we've got a couple of models. We can upload it to Cosmos DB, which is great because we can also then, the app can do very quick queries against it as well. Or it can be or just be Azure storage. So it could be just blob storage. And then it goes into a pipeline, and I'll talk a little bit about that later, where we kind of clean up the data, we kind of canonicalize it. And then once you've got your data, you can use Power BI, you can use machine learning to gain insights into it, and then you feed back and use analytics, and you feed back to the coaches or to the consumers insights into how they're skiing. And skiing is the one we've chosen because A, we like skiing, and B, it's an interesting application area. It's also hard. But really, we see this as being applied to all kinds of sports and indeed health applications.
So you've tested this a lot yourself?
We have been testing this a lot ourselves, yes. And the good thing about machine learning is once you kind of figure out your algorithms and this sort of thing, as you may well know, what you have to do with machine learning models is you train them, and by that you give it a lot of training data. So you give it examples of data of particular kinds of turns. So what we have been doing is going out. Our working day at a typical ski resort is we get up and have breakfast. Some of the guys might even have been up coding a little bit, and then we instrument the athletes, which actually is us. And then we might load a new version of the app onto our Android phones, stick it in a pocket, and then you go skiing for a few hours. But we might have the task for the day might be we need to do snowplow turns, or we might need to do slow skidded turns, or we might do short, fast skidded turns. Skidded turns is actually the only one I can do because I'm a very moderate ability skier. And then on the occasions where we need to do carved turns, then we send the experts out, and they do these beautiful carved turns. How many skiers have we got in here? Yeah, so you know what I'm talking about, And then we go out and we're gathering data, and we're kind of getting good quality data, which we then feed into the system, and we use that to train the ML models, get them, because ML really, and I'm not an ML expert, but as far as I can tell, it seems to be basically detecting patterns. So it's kind of, you give it lots of examples of certain things, and then you give it a random live data, and it comes back to you and says, oh, that was a pretty good, carved turn, or that was a snowplow turn, or, you were leaning too far over to the right, and these are the kind of insights we're trying to get out of it. And Kevin Ashley on our team, this app, Winter Sports, is actually available. It's a Xamarin app, so it's available in the iOS store and also an Android store and indeed Windows store. And this app is uses it has different modes, so it kind of uses the accelerometers and the sensors you've got built into a phone. It uses them if you haven't got any high definition sensors, but it can also be configured to work with these guys to actually get more advanced, interesting turn measurement and G-force analysis and that kind of thing. And this is the first kind of actual real example of an app that uses this sensor kit stuff. And what we're doing is the sensor signals, you can actually provide, you can get interpretable activity signatures. So you can identify these patterns, and you can you can take sports analytics onto the next step. Once you've got all this data with the power of machine learning, you can go beyond simple measuring how many meters of ascent you've done, which interesting though that stuff is, we want much more than that. So instead of just basic simple tracking and aggregates, we can actually start measuring elements of a skill or activity. The technique, you can start looking at angles and speeds and this kind of thing, and using machine learning, comparing expert skiers against the input samples. You can start to sort of measure how the quality of skiing and how people are doing it. So we modestly think this is the analytics of sports redefined, and a lot of top coaches are very excited about this as well. And this is why we're working with the United States ski team and a bunch of other people in the industry who are very interested in seeing how far we can take this. So we built, part of a sensor kit is actually some reference hardware. So one thing we found when we started doing this is that actually commercial hardware that's out there available often doesn't kind of have enough of the features that we really want for this to really work well. So part of it is to have this reference hardware, and these things basically are built by a guy on our team who goes into his workshop in his garage, and he produces these, gets his soldering iron out, and it's an Arduino sensor, and he has a little bit of storage in there, and he solders on a battery holder, and he actually hand builds these things. But the idea is this is reference hardware that illustrates the key features that you're going to need for this kind of thing. But in general, what a sensor is, it has in it a thing called an IMU, which is an inertial measurement unit, which is basically a little very powerful sensor on a chip, which an IMU is capable of providing 9 degrees of freedom. What that means is basically it can measure at a high frequency X, Y, Z, so in 3 dimensions, X, Y, Z of accelerometer, gyrometer and magnetometer, and that's all built into it. And this is off-the-shelf electronics here, these chips that do this, and typically at 40 to 100 hertz, so you're getting very high frequency, lots of data being generated. These devices must have Bluetooth LE, so you can actually communicate from them to the phone app, and they'll need some kind of storage adequate for kind of aggregating or buffering data so that the phone can pull this off in near real time. So you can have some kind of storage. And it may have other sensors such as proximity, location, and that's and so forth. But the key things is this IMU9 is the key kind of thing, and the high frequency is the other key characteristic of these things. Now, so I joined the project, and we very early on we went up to Finland to Helsinki, well actually Varta, and we went up there to visit Suunto. Suunto make diving computers, and they also make compasses, and they're part of a bigger group called Sports that we're working with, who also own Atomic skis, and they own Mavic bikes, and they own Salomon skis. So we're working with Sports. And they a little while ago they have the dive computers, and they have the electronics, they've custom hardware that they've developed that work in these dive computers. And they, some time ago, they kind of had a little side project and thought, well, what if we took this little computer, the electronics on this, and packaged it up and actually tried to develop and sold it, manufactured these in large volumes, and decided to try and build a developer community around it. And the result was this Movesense sensor. which they has been through various iterations. The current hardware is the G1 variant, which has this thing around here, and they are very successfully building a big developer community around these sensors. And like they're a partner of ours, so they have got a whole bunch of software samples and that sort of thing, but only for Android and iOS. And so we talk to them, and they are very keen, and obviously we are very keen to extend the usage, the easy development of applications for these things out to C# developers, to .NET developers. So that's the bit of the project I got involved with. So this also has a 9-axis IMU in it, has quite a lot of memory in it actually. 2 megs, 4 megs, I forget. It has a lot of inbuilt memory, which if you're logging at 56 hertz, which is the kind of what we like to monitor at, is enough for around about 3 minutes of data, which is not a lot, but enough for a ski run probably. Well, not the longest ones. You can update it with Bluetooth LE, the firmware on it. They're very lightweight. They also have this connector as well, so you can easily clip it onto clothing as well. So you can add on these additional things like a heart rate monitor onto it. So they're pretty versatile, and they are really trying to push the developer community. And they hold meetups in Finland, and they travel around as well to other big shows. We're developing a relationship with them. It comes with a whole bunch of software libraries for building compatible mobile applications, but they only support the Android and iOS. But I have built now this C#.NET, and I'm going to take you through what it is and how you use it. So before I do that, let's just give you a look at the resources they have. So if you go to movesense.com, this is their homepage, and over here you can actually go off, and they have a shop where you can buy a developer kit. And the developer kit, you get 2 sensors and a strap, and that's only 99 euros. Or you can buy one of these at 39 euros 50. Your clothing clips and strap holders and all this kind of stuff. So that's the shop where you can buy the hardware. So it's really cheap to get started with these things. There also will be at sometime a programming jig on this, which I'll talk about why you might want that. And on here then, so you can get yourself kitted out with some hardware. And also there's links on the developers bit of it as well. So obviously this is where we're going to start if you want to start developing for these things. And it gives you an introduction to the platform. Tells you to get the developer hardware kit. That takes you off to the store to buy your hardware. And then you need to install the developer environment. And it gives you a link to do that. And then you also need, so here's the first thing, you need to actually have, the thing about these is when you buy them, these guys, they're absolutely, oh, another battery. They're actually useless when they come out of the box. The other interesting thing about these is they need to have an app running on it. The app encapsulates the firmware. So this is the app actually has the built-in, basic functionality that allows you then, once an app is running on here, you can then use their REST API from your mobile app to talk to the device, and you can then start reading data off the inertial measurement unit, off the sensor and that sort of thing. So the first thing is you need to actually install on this some kind of an app. And this is actually one of the interesting kind of selling points of this sensor, is that you can obviously, it's C++, you can develop in Visual Studio, you can actually write your own applications to run on this guy, to have your own custom scenario. So they provide a bunch of sample apps, and to get going you just need to build and install one of these little sample apps. So So this takes you to their documentation. It's all up on Bitbucket, all of their stuff. There's some list of the different APIs. This is the REST API, so you can actually kind of go to the accelerometer, you can go to the ECG, the gyro, the heart rate monitor, basically the IMU, synchronous access to that, the magnetometer on its own, temperature data. If you've got the temperature, the thermometer add-on on it, there's a data logger, bunch of great stuff. This is all the API surface. And then it takes you down here, and actually this is how you need to set up your machine in order to get come on. Zoom, it's not working. Okay, never mind. This is how you set your system up. And now my mouse has stopped working. Oh, I shouldn't have hit zoom it. Oh my gosh. Okay. Let me zoom this in a bit more so you can see. So the manual setup, they talk about, there is a virtual machine thing you can set up, but I've always done this. It gives you all the links to the software you need to install. There's a GNU toolchain for ARM embedded, where you install that stuff. There's something called Ninja. You have to download that and stick it in a folder and make sure that you set the path set it into your path variable so the build tools can find it. You need something called CMake, and you need something called NRF-util. So Nordic Semiconductor are the guys who really are the Bluetooth LE experts, and their software is running on these devices. A lot of sensors use their stuff. It says you need a Visual Studio redistributable. You don't, just install Visual Studio 2017 and you're away. That will have the bits that you need. So you install all of that stuff, and then you need to go off and you have to compile the firmware. I'm going to actually just run you through this, and then it actually gives you an example application build flow. So what you need to do basically is clone this repo, which I've done. Let's go off and find GitHub. So I've cloned the device lib. So that's all the stuff in it. I'm just going to copy it and go off to, I'm going to create a new, I'll go off to test. I'll drop my copy into there. And then what you do to build the firmware, once that's copied, you create yourself a new folder in there called something like my build, and we go off into there. Nothing in there, of course, at the moment. Now what we're going to do is we actually basically are going to follow these. We've basically done all that, and then we're going to build a debug version or a release version of the selected sample application. Now the key to do this, and this is all of this stuff here. The key to doing this is actually to open a Visual Studio command developer prompt so it can find the C++ controller. So I'm going to go off down to, oh, actually I've got a developer command prompt thing on my start page. So I'm going to open that. I need to go to that folder where we just were. So it's my build. Let's get the path to that. Control C. Back on that. I'm going to CD to that folder. So now we're in the right place. And then before I build, I need to build one of the sample apps they provided. And if we go just back up here before we do that, you see the samples are all in here, and they are documented in the docs. There's actually quite a bunch of them. So there's an accelerometer app. There's a Blinky app which just blinks the LED. There's Hello World, which creates a custom service that you can connect to. There's a heart rate wake up, which is interesting. But all I want to do is just do the plain app. Now there's one thing. There's a kind of gotcha with this, in that when you if we just go into code and go into app.cd, I'm going to open this with Visual Studio Code. The plain app has very little in it. But what it does have is down here is a serial communication true. And there's a warning in the docs as well. This is if you're using the jig, which if you're doing hardcore development on these devices, you get a fancy jig and you plug the sensor into it and it has a power supply, and this is what real embedded developers do. You don't need to do that, and if you are going to do using the jig, then you need the serial port enabled on the sensor, because then you connect to it, but then you're working on mains power and that sort of thing. But generally, if you're going to work on these little batteries, you need to change that to false, so that you turn off the serial port, because otherwise you just burn your battery when you're running it. So let's make that change to the plain app. And now I'm going to build a release version of this. I'm going to copy the first bit, paste that into there, and then scroll to the right and get the rest of it. So this is the and then I'm going to do the plain app rather than the Hello World app. Plain app. And we're going to build that, and this is actually going to compile the firmware. So that builds into it the firmware that they release, and also on top of it the application that is going to run on this little sensor. So you have to do this first. Doesn't take too long. And then the next stage I'm going to do, at the bottom of the page here, you can see if you want to update the sensor over the air, you do Ninja DFU PKG. So I'm going to do that as well. So it's all documented here what you have to do. Ninja DFU KPG, and that does a bit more chuntering and runs loads more of their tool chain. So if you've installed everything correctly, this doesn't take too long, and it creates for you a update package which you can then update over Bluetooth LE to update one of the sensors. So this should be done in just a second. And what you get out of this, and you have to keep an eye on the Bitbucket site, because they update the firmware every so often and they fix bugs. Okay, that's actually created everything I need. So if we go back up to the My Build folder, you see what it's creating here is 2 zip files. So the package is just a zip. There's 2. It actually creates 2. There's a Movesense DFU and a Movesense DFU with bootloader. There's a bootloader on these devices and the actual package, and they change the format of the bootloader. So if you've got one of the older versions, previous to version 1.3, you have to install this one. If you've already installed the new bootloader, you can just go for that one. Now, how do we get this onto the device? Well, so part of the stuff that's up on Bitbucket, if we scroll back up to, this is the breadcrumb where we are. So we're in Movesense Device Lib, which is the software that runs on the sensor. Go up to Movesense Community on Bitbucket. That's the one where we just were. There's some docs, Movesense docs, so you can go read the docs. But this one down here is their other repo, which is the mobile lib. This is the sample apps for actually running. This is like the Android and iOS sample apps that run on your phone that talk to the sensor. And in here, you download all of this, and they include in here, and there's also instructions on how you build the example project for iOS and for Android. And then there's a little bit about the firmware update. So basically you have to download all of this as well. So, and then it's just like, honestly, if you ever wanted to be multi-talent, multi-skilled and this sort of thing, the number of different software applications and things I've had to use for this. This is the world of the IoT, the embedded hardware developer. So I now have installed Android Studio. And Android Studio here I've now built and compiled the sample app that they provide and installed it onto my Android phone here. Okay. Right. So I'm mirroring my my Android phone here, and what you get is this Movesense example app, which I'm now going to just start up. And there's a whole bunch of stuff, including on this, you can actually go and use the Movesense. You can start scanning for a Movesense device in here. And it shows all of the sensors, and this one is, I'll just get my glasses on so I can see. Unfortunately, I've got about 20 of them in here, and they're all alive, so I need number 14, which is actually the one at the top. So I'm going to go 14. It's connecting to this guy. So you can actually sort of see what a sample app can do, and this great. And so let's have a look at the, and it tells you it's got version 1.4.0 on it. And you can we can go off and do the linear acceleration. So you can subscribe to linear acceleration on this device. So we're going to, you can see now it's actually recording it. The sensor is motionless, so there's nothing much happening. But if I start waving it around, you can start seeing we're getting the X, Y, Z for the accelerometer data is being transmitted over Bluetooth LE to the app running on here. Basically, my mission is I want to do the same, but my app I want it to be written in Xamarin. I want it written in C#. I want us to have all the same fun that these Android devs have got. And honestly, have any of you done any native Android development in here? My God, what a lot of code. I mean, Jesus, you look at the source code for this thing in here. With .NET and Xamarin, if you start doing MVVM, as you all know, the number of files kind of mushrooms. And this sample app has beautiful architecture, but my goodness, what a lot of stuff. But anyway, I've gained a kind of a respect for Android developers by looking at all of this. But it's a load of stuff, and I've had to spend a lot of time analyzing this sample app to figure out what it's doing with the underlying MDS library so that I could implement the same thing on C#. So I've spent a lot of time researching this app. Now, this, so that's the linear acceleration. So you can actually execute the different things, the REST API. You see all the different things you can do on there. And I'm going to exit this one. But the important thing from the point of view of what I was just talking about, which is the firmware, is this is where you can actually flash the device. So now the way you saw me before using the command line tools, and I built those zip packages. Now what I do then is I use good Microsoft tools. So I actually then copy those zip files onto my OneDrive. And then I use the OneDrive app on the Android phone to actually then I can go off and I can go and find open my OneDrive folder, which is synced to the Android phone, in order to get the actual software. So I'm going to choose here the zip I just created, and now I'm going to select the device I want to update. I'm going to select number 14, the one that which was running 1.4.0. I'm then going to hit proceed, and this is now going to flash that device with the latest version of this app. We want to update it? Yes, we do. And it's now starting the DFU mode to update. It's going to upload the new version, that zip, onto the device. It takes a few minutes, and that's now going to update this firmware on this device to actually 1.4.1. They had a little bug which was in 1.4.0, which caused the battery to run down. It got into a tight loop. So I'm now upgrading it to the 1.4.1 version. And that's how you get the software onto it. Now down the road, one thing I'm going to do with this project is start writing my own apps to run on the phone, which means I'm going to have to dust off my C++ development skills, which I used to do back in, when did I last do it? We're talking about 17 years ago. I was a C++ developer, so this is going to be painful for me. But hey, they're all the same. These C-based languages, aren't they? So it'll be fine. And I'm going to actually what I want to do is start writing applications that are running on the device that can do some of the analysis that we currently what I'm doing basically is getting raw data, uploading it to Azure and doing all the analysis in the cloud. But that's a lot of data is going over Bluetooth LE, and as you well know, with Bluetooth LE. It's not the most reliable thing in the world. It does let you down. So if you can actually reduce the amount of data that you're transferring over the air, you've got a better chance of success. So what I want to do is have software running on the device that's talking to the accelerometer that's going to aggregate the data, and then the phone app can pull that aggregated data off rather than the raw data. So that's kind of on my to-do list. And down the line, we can actually, with the move of IoT Edge, it'd be nice to actually run machine learning models on the sensors. You know, simple stuff. We can actually do some analysis in real time from the raw data. So there's a lot of scope with being able to run software on the device. There's a lot of interesting scenarios that opens up. But for now, I'm just using the plain app, which basically has no functionality other than supporting the basic REST API, the functionality. So that's 98%. So that has uploaded, and now that has updated that sensor. So I've now got a newly updated device. So that's how you flash the device, how you get it working, and that's an important part of the whole process that you have to go through in order to do all this sort of thing. Okay, so that's phase one. So now we've got some sensors, we've got the latest version of the firmware on them. We've got a very detailed Android sample app that we can examine. So the next thing I wanted to do was, and when you look at this application, what you find is that if I go back up to GitHub, the other repo, the mobile lib, in Android, there's the samples, but up here in Movesense, when you look at these samples, you realize that all of them use a library, which is in this thing here. Okay, there we go. So actually, Zoom it is working. I did the wrong key before. Which is this? This is the latest version of the MDS lib. So the MDS lib is their low-level API. It encapsulates the REST API. Every app that you build that runs on Android uses MDS lib, or on iOS uses the iOS version of MDS lib. So MDS lib is what Movesense have created to enable application developers to be able to talk easily to these sensors. So that's the guy we want to use in our .NET land. So the process for this, so that was kind of getting started. Yeah, so the process for this to build the .NET version of this. So I want, this is kind of fun, this world, and I want the same fun to be available for C# developers. So what we need to do is take that MDS lib and have any of you, how many of you are Xamarin devs in here? Have any of you tried to build a bindings library? Oh, good. See me afterwards, I've got work for you. Yeah. Did it go smoothly? Yeah. Yeah, both the same, yeah. As it says here, binding an Android library. So the thing is, if you're in this world, there are a whole bunch of native Android libraries that people have created for various reasons, which can encapsulate very useful functionality. And rather than reinvent the wheel from scratch, in the .NET land, wouldn't it be nice if we were able to take those existing libraries and call them from C#? And that's what a bindings library does. You wrap a native library, in this case it's the mdslib.aar library, and we use some tooling in Visual Studio to create around it a managed callable wrapper, which is basically a runtime callable wrapper. It's kind of, you wrap it in C# .NET callable stuff. Rather like, I suppose, WinRT kind of does that sort of thing as well. It's a runtime callable wrapper, but this is the Xamarin version. So, but in the heart of it, and you can do this with native Android libraries, and you can also do it with native iOS libraries as well. So what you can do then is build around it this thing that's callable from C#. So now we can actually call into MDSlib from a C# layer. But as it says here, binding, and this is taken straight from the official documentation on MSDN, binding an Android library, an AAR or a jar file, is seldom a straightforward affair. And I can vouch for this. It is a complete pain. Under C#, under Android, there's all the blank app Androids, Wear app, WebView app, OpenGL game, Class IB, and down here is this bindings library. This is the one which I'm going to create that in C temp and call it Movesense binding library. So we create this binding library. It's a very simple thing. Has a few folders, and it has an about jars.txt, which just gives you a bit of information on what you can do. And it basically says plug your input jars into here and your reference jars. It doesn't say anything about AAR, so immediately you're off in the documentation thinking, oh, this doesn't look like this applies to my situation. But actually it does. So let's go off to Movesense and copy that MDS lib. Copy it, and you drop it into your jar folder. Pop it into there. And I'm going to include it in the project. And you have to give it the appropriate build action, which is it's a library project zip is the one that you use for an AAR. There is a walkthrough of a ridiculously simple example in the Xamarin docs that make it look like a breeze. You know, it's like this. It's like a library with one class and one method in it, and you know, you think, oh, how hard can this be? So you follow their instructions, and it basically says, okay, yeah, you just plug it in there, library project zip, and then you build it. So you go, okay, let's build this and let's see what happens. So you build this thing, and it's chuntering away. And you get a whole bunch of errors, of course. So let's have a look at some of these things down here. Well, you get a whole bunch of stuff that says member names cannot be the same as their enclosing type. Another one of those. Error event args already defines a member called constructor with the same parameter. Then type error event args already contains a definition. And then some types don't exist. And this all looks, and at this point it dawns on you this is not going to be as simple as the example in the documentation. No surprise there. But there is actually, usefully, some documentation that's quite helpful for this, which is this section in the docs, which is troubleshooting bindings. And there's some helpful things in here. It tells you might need some external dependencies and this sort of thing. You might want to decompile your library and go and have a look for dependencies, and you're thinking, uh-oh. You can inspect API.xml. It tells you, it generates this XML file. You can go and look in there. It does warn you. It says the contents of this file can help identify any missing types or methods, duplicate binding. It says, although inspection of this file is tedious and time consuming. You're not kidding. Oh my God. So I did try looking into this file, but honestly, life's too short for this. So you go on, but then there's this known issues, and some of this actually did yield me some useful things. Missing C# types in the generated output gives you some reasons why that might happen. Parameter type mismatch. Okay, that sounds a bit like the one we saw in there with the P0 parameter type mismatch. And then, okay, duplicate customer event args types. Now that's definitely something that actually, when you go back to where we were in Visual Studio, error event args and this sort of thing, some of these kind of does look like some of the examples we got here. Anyway, long story short, I spent a very long time trying to get this working, numerous emails to people in Xamarin team in Microsoft and this sort of thing. And essentially what you need to do is start putting some stuff into this metadata file here. And this is some kind of rules that that kind of tells the bindings generator, don't bother with that, or treat this differently, rename this, and all this kind of jiggery pokery you have to do. And I'm not going to bore you with all the details, but what I am going to do is just go and find the oh, hang on, that one. Yeah, here we go, snippets. I've got here a bunch of XML, which I'm going to plug into here. And what this is doing is, I had two event listeners having the same named event, and I figured out I had an MDS notification listener and a response listener, which both had the same things. And then I also had some fields, generated member name being the same as the enclosing type. We saw that error down there, so you can actually rename things in the generated code as well. And then the other one, I got some errors down here, which was MDS unregister operation, threshold class, no suitable method found to override, and the IMNDS response handler and MDS operation, all this sort of thing. Anyway, it turns out that all of that is because there's something that I don't understand is wrong with MDS unregister operation. But there's also one good thing about this thing is that the MDS lib is this huge library. You don't necessarily need it all. So I've actually taken the executive decision to completely remove from my generated thing MDS register operation and MDS unregister operation. And in my sample app, I haven't needed it yet, but I got this feeling this might bite me down the road because I think I know what that's for, and it is something I'm going to want to support in the future. But anyway, I've pushed that one to one side, and if we build it now, then we hopefully have sorted out all our problems, and I have a clean compiled Movesense binding library, which allows me, if this builds successfully, yes, one succeeded. So I've now got my bindings library. I've now got a C# callable version of MDS lib, which I can then build my .NET API on top of, which we will come to. There's one bit I didn't talk about, that is also you need to kind of also find out dependencies on it. So you have to go and look at the Android source, and you're looking for things like if I find well, this, if you look at, for example, at the Gradle script to build this, you can find that there's other kind of dependencies that you actually kind of have to consider sometimes adding into a library. And to get all of these, the MDS lib has a dependency on another Android library called RX Android BLE. You basically have to do a lot of detective work. So there's a thing that Android devs use. So they pulls all the dependency packages, and you just put basically a sort of include statement into your Gradle.build file, and it pulls them down from Maven, very much like NuGet. And you have to go off and look for let's see, RX Android BLE, for example, which was the library that things, and it finds the matching thing. And if you drill down into these, you can kind of also find that itself has some dependencies. So you look at the project object model, and you can see that it also goes for a thing called io.reactivex.rxjava, some Android support things, something called RX Relay. So you're doing all of this detective work, and the end result is that you end up with a bindings project which looks a bit like this. So we've got the MDS lib in there, we've also got RX Android BLE, we've got RX Java, we've got RX Relay, and all of these other guys go in as kind of dependencies. They have an embedded reference jar, which means the bindings generator doesn't try and build C# bindings for them, but they're kind of included in as embedded resources, so that when you make a call to MDS lib from your external C# code, it can call into it can find the dependent Android libraries that it itself is referring to. So it's a lot of work, and it's not easy, but at the end of it, I finally have a Movesense binding that works. So I'm going to collapse that, we're good. Now I'm just going to, so then I wanted to build basically a C# library around this, a new programming API, a higher level abstraction to make it really easy for C# devs to use the underlying REST API. And the only way really to figure that out is to go off and study the Android app. I mean, if we look at the linear acceleration test, you can kind of look at this this code here, and you can figure out that the path, the REST API for acceleration data is this MEAS/ACC. We have an event listener URI, which is Suunto MDS event lister, and basically, you know, you kind of you just got to study this stuff. And I've, like I said in the first half, I've got a understanding of Android code, simply enough to understand how to call the MDS lib APIs. And this is a good example here. You have mds.builder.build. So the builder is a method that's in the MDS lib. Builder.build, you've got to pass it the context of this, which is the current activity in Android. And then you get this, you're using REST methods. So get, put, delete, you know, the usual REST methods. And then you're getting a particular URI, which is the URI mdsrx.scheme prefix. You need to put the serial number of the connected device, which is its Bluetooth serial number, and the path to it. And anyway, and you give it a MDS response listener, which is called when we actually connect to that device and get the data. So honestly, a lot of work. The end result, though, and this was months of work, is which is the sample app, which I'm going to ship with the SDK when I open source it, which will be at the end of the week. So I've now, in the bigger solution, I've got my Movesense binding library. I've got a thing called SensorKit, which is which is part of our SensorKit API that I introduced at the beginning. For that, it's got some view models in it. It's got some Bluetooth LE connectivity stuff that I'm making use of, but that's kind of open source. And then below here, Suunto log Xam. This is the shared library for a Xamarin Forms. This is my sample application. And then this is the actual native Xamarin Android app. So obviously on my to-do list is to expand this out to iOS as well from Xamarin, but for now it's just Android. In a Xamarin Forms app in the Android, there's basically nothing in the activity in the native thing, other than requesting permissions. I need to ask for access find location because I'm doing Bluetooth LE stuff. There is also, I'm using a thing called Oxyplot, which is on NuGet, which is I'm using for graphs. That Oxyplot is a C# cross-platform library for doing graphing, which I have used in this, which is working really well. So that's the only thing that goes into the core native API project in it. Everything else is in the shared library project. And the key things that I'm going to call out here is this is my wrapper for the MDS library. I've got an MDX, which is just a get instance thing, which is MDS instance, which is a singleton thing. I've got a connection listener, a basic one for listening to connections. I've got a similar one for connection service. But then all of the API calls in the REST API are all encapsulated. I've got a base class called API call async, which is for a call that doesn't return anything. Or API call async T is the base class for every class I've got in here, which basically has the plumbing and a lot of .NET-y stuff, task completion sources and this sort of thing. But essentially the method on here that's important is perform async. And all of the API calls in here, for example, get time, for example. Oh no, get battery level. There, I can get the power of things. I have a class and they all follow this pattern. They inherit from API call async of T, where the T is the type of object that gets returned. So a battery result object is defined down here in model, which is simply a class that's serialized to JSON. So it's a JSON serializable object, and you get a public property called mCharge%, and I've put a method on it called getBatteryLevel, which is just a convenience method to actually get that. But going back to get battery level, so to use it from an application developer's point of view, they construct one of these get battery level objects. This I might get rid of actually. Because when you retry it, you can actually cancel it after a number of things. So, and then I have this perform call, which simply does the MDS dot whatever get of the whatever the URI is, and this is the paths which I've basically copied from looking at the Android source. So but this is the whole of the REST API I have wrapped here. There's a few missing. I still haven't, there's a few more I have to add, but creating a new one of their REST APIs is as simple as creating one of these objects. So that's all the work that I've done for the developer. In terms of the actual application, if we look at, for example, I've got, if we're going to get linear acceleration, for example, I've got a XAML page, a Xamarin Forms XAML page, where we've got a select the device button. I've then got a switch to actually some UI here to actually subscribe, and then I have a plot view, which is the Oxyplot container for the graphing stuff. So essentially, what I'm going to do here is we go off to over to here. This is this application I've created. I'm going to go off to subscribe. This is the exact page that we were just looking at, the XAML that's just behind. I need to select a device. I'm going to find one of my devices. So I've selected a device, and then I can subscribe to linear acceleration. It's connecting, it's doing the Bluetooth LE connection, and then it's doing the MDS connection to set up the logical connection to the sensor. And now it's subscribed, and it will start in a second. It will start. We obviously it's motionless at the minute, so it's flatlining. And then if I shake the bag, yeah, you can see obviously we've got some data coming out there, and this is all being plotted by Oxyplot, which I try. Have any of you used Oxyplot? It's open source, created by a bunch of MVPs. Recommended actually, completely free. And it's cross-platform, works across all the different flavors of Xamarin and also UWP and that sort of thing. So that's essentially the same as we saw in the Android app, but this is a completely C# and Xamarin application. Just a little bit about, so we look at the code behind this, the linear acceleration test page. I'm going to look at the view model. And it's a standard MVVM view model. I've got a device scan service that we inject into this for doing the scanning of devices. I've got a Xamarin.Forms command, which is effectively the event handler for when we subscribe, switch on and off, which has the logic in it. And actually, this is using the API. So first of all, I sensor.connect, so that's just connecting to it. And then I new up my linear acceleration subscription. And then I call the subscribe async method on it. So it's a fully nice async, modern .NET API. And then the parameter for subscribe async is a call to a handler method, which is this plot data, which simply is all this graph stuff down here. There's some scanning stuff, finding the devices, but then here's the plot. This is all Oxyplot stuff. We have a model, we have the XYZ draw line series, then we initialize the plot model, we add obviously a horizontal and a vertical axis. This is how you use Oxyplot, nice and easy. And then we add the line series to the model, that's the initialization. And then this plot data, this is called on the event handler when we're getting events while we're subscribing. So every time we get a new accelerometer reading, we're calling this method. We're checking the initial timestamp, so we're normalizing it down so it starts at 0. These devices, they have a timer on them, a timestamp that runs from when they were initially started in milliseconds. So that could be days ago or weeks ago and this sort of thing. So I need to actually obviously normalize it. So I capture the very first reading, and then thereafter, for every time we get a new reading, I subtract the timestamp of the first reading off the new one we've got. So we get the actual time normalized based on 0. And then I simply add the X line series, Y series, and the Z series points to it, and that's and then you invalidate the plot, and that's all you need to actually draw that graph. So nice and easy. And that's, so you saw, I just want to stress that again, the programming model for my API, which I'm a little bit proud of, is basically this: connect, create a subscription object, and subscribe. And then when you're done with it, you can unsubscribe. This is so much simpler. And one of the feedback we've been giving to Suunto and Movesense about their API is that it's way too complicated. At the moment, the Android and iOS devs have to write rafts of code, and we've brought it down to a few lines of beautiful .NET. And you being the .NET North user group, you will appreciate the beauty of this and sort of things we can do. So that's really nice. So that was now this is at the moment it's Android only. So on the to-do list, a couple of things. First of all, we have built the bindings project for the iOS native MDS lib as well. So I need to refactor it, and we need to support iOS as well, iOS and Android. And then I want to package the whole thing up as in a NuGet package, what do you call it? Hook and bait? Bait and switch, that's right. So it's going to be a bait and switch thing, and I'm going to Seattle the week after next, and we're going to have a little project where we're going to do this work and then open source the whole lot shooting match. So it'll be good for that. We obviously would love to extend this to UWP as well, but we haven't got a native UWP MDS lib at the minute. So I need to talk to my friends at Suunto and see. I haven't actually got the source for MDS lib, but talk to them about doing this, adding Windows in as well. It's a sad fact that it's not going to be in there, but at least if we extend it out to Android and iOS, then we're covering a good number of potential users. I just want to talk a bit more about this stage. So we've now got an app which we can write in Xamarin Forms or Xamarin Android, and like I said, Xamarin iOS will be coming, and we can now pull all this data off. But what a bit more about this data. First of all, a little bit about data collection options. What we're basically doing at that with the subscribing is we're getting raw data from the accelerometer. So we're getting raw logging, if you like. If we start running some simple analysis in that C++ code on the device, then we can start doing some simple analysis ourselves right up front, because you can actually have an app running on the phone that's pulling data. You can also have an app running on the device itself that is using the same REST APIs and analyzing the exact same data, but that gives you the opportunity to identify some events in real time, such as turns or jumps and so forth. So some data analysis we can do right up front. And obviously this is event level data, and the advantage of this is that we're not requiring all that raw data, which is very high frequency, high volume, to go across the Bluetooth LE. So we're simplifying the comms, we're making the whole solution more robust, and instead we can signal. One thing that you can do with these sensors is create your own custom REST endpoints on it. So you can actually create your own service, and you can publish your own events through that REST API. So it allows you to extend it very nicely to support more than the basic functions, which is a very full set of functions that they support in the REST API. You can extend it to your own custom ones as well. So that's event level data, which we want to do, but that needs obviously some C++ programming and that sort of thing. And then the other thing is also we can do summary data, so you can aggregate on the device as well. And then you've got a relatively small payload for data transfer. So that's something we want to do. In addition, data may be collected in near real time or collected intermittently. So one thing that the app does as well is supports another couple. It's much more sophisticated than that. The other option on the home page of this is to pull logs. So this does support a data logger as well. So you can actually also now, with this, we can support a group of sensors. So I'm going to say, okay, I want number 14 and number 610. I'm going to add them to a group, new group called, let's call it test. Okay. So we've now got a test group. We've got a group of sensors in it. And we can actually turn them on as a group, but we can also enable the on-device logger. So what this is doing is now it's going to connect to each of these devices in turn. We're going to enable the data logger, and that's going to use the native storage that's on the device. And you can run this, as I said before, at 26 hertz, you can run it for about 5 minutes. At 52, which is actually our preferred, you're down to sort of 2.5 to 3 minutes, which is only just enough really for good data analysis. But you can actually turn these on. We actually get the battery as well, and you can set these things off running. And the idea here is you're in the ski lift. You get to the top of the run. You've already got a couple of sensors on the. We like to set them below the knee because on a ski the foot is in the ski boot, which is attached to the ski, and that is all. It's all rigid, all that. So you've got a very firm connection between the ski up to the knee. Once you get above the knee, then all of a sudden you've got human limbs in there, and all bets are off in terms of getting meaningful data. You can actually measure things like the tilt of the body and that sort of thing. But in terms of getting the actual skis on the slope, you really need your sensors down as near the feet as possible. Okay, we set off now. Now we are logging. So the idea is you set a group of sensors off at the top of the slope. You ski down a piste and this sort of thing, and all the time the logging is going on and saving the data on the device. So the phone isn't involved anymore. And then you get to the bottom and you finish the run, and then you turn them off again. And this stops the logger, turns them off, and then we can I can hit the get logs thing, which actually starts a background task to upload the pulls the log files off the sensor and uploads them directly to Azure, into Azure storage. So that's the other model. It's a pull model. So we support all of that as well. So that's the multiple sensors thing which I touched on there. So you can start putting different ones, but then time synchronization becomes essential as well, because you've got to have for meaningful data from multiple sensors that you want to amalgamate together, you've got to have the time has to be identical on all of them. We can do that. There's a set time and a get time method. But I'm going to need to also write another custom service just to make sure that we've got a exact synchronization between the clock on the sensor to be able to map it to the clock on the phone. So there's a little bit of thinking about that as well, about combining groups of sensors is kind of challenging as well. I just did that demo, so I think. And then ultimately, so I've been focusing all on the client side. Ultimately, what we're doing is we're building it into a big old pipeline. There's a whole bunch of stuff in Azure that I've not touched on here. And the idea is that we're going to upload this data to Azure. It goes through a data ingestion pipeline. We do a lot of data processing to normalize it. So all the data then becomes standardized into a canonical form. We can then run our machine learning models against it. We get insights. And ultimately, it comes back to the remote coach or the end users in terms of meaningful dashboards of data or in the app. So the whole opens up a whole great opportunities for exciting consumer-facing applications or professional coach-facing applications. And just to drill in a little bit of that, this is the data processing we've got in Azure, and there's a whole team of people working on this side of things as well, where we're ingesting data from different sensors. We're pouring it into data lake or data warehouse, or we're doing some processing on it. There's Azure functions in there as well to do really quick processing on the data to normalize it all, and then spits out at the end, and we can start using Power BI and to send back the data and do analytics on it. So there's a whole bunch of machine learning going on there that's key. Just to give you an insight into some of that processing that goes on. So in order to quite a simple thing is detecting turns, actually. So one of the things we've been doing is detecting turns. The other thing we're doing is detecting G-forces through a turn. That's much more complicated. But turns itself, turns out actually detecting how many turns a skier does is relatively straightforward. And you only need data from accelerometer and gyrometer for doing that. And it turns out that when the skier is we're obviously only interested in terms of measuring that when the skier is actually moving. So we're not interested if they're sat on the ski lift. We're not interested if they're stood there chatting to their mates at the top. We aren't interested when they're actually skiing. So we need to be able to detect that. And this is what we've been doing all winter, is figuring this stuff out, you know. It turns out that obviously when the athlete is standing still, the accelerometer is flatlined. You saw that in the graph data I was showing you before. But angular velocity may be changing. But so even sat in a ski lift, you know, they're just sat in a chair. You get some movement in some of the data, but not in others. Then when they actually start moving, you get the amplitude of the acceleration and the accelerator and the gyrometer value just change very rapidly. So it's a pretty easy job to define a threshold and ignore everything where the data is below that threshold and only interested when it's up above. So this is a dashboard for working with R scripts, and this has been given to me by one of our data ML people. So we've actually got this is all R code, which is the kind of thing that they do for processing all of this data. And if I could just, I've got already a file with loads and loads of XYZ accelerometer data. It's megabytes of the thing. It's huge, and I can just run this first method, which is to load in read the new format file. We've got a plot single chart function which we can compile. I've got plot initial charts function which I can also compile. And then this is the meat of it. This is where it's actually going to read a file which is in C-test sensor kit data. And it's called 2018 01 14 13 14 31 carve.txt file. So this is raw data file we've got out of one of these things. And then I'm going to just run this, and it will analyze masses of data and run this, and it's read in 14,820 rows of data. It's processing at the moment. We're kind of figuring out the important data in that, and this is an R script. Now this is the kind of work that data scientists do. They're analyzing all of this data. Once you've got an R script that's proven and works, so they kind of work with this at a simple level like this. Then you can incorporate that into a machine learning model, and you can then start feeding it with lots of data, and this becomes the processing that. Okay, there it goes. It zoomed in, it didn't reset. And then this is plotted these charts, so you can see this is the kind of data analysis we've got. Sorry about that block down there, it seems to be stuck to the screen. So we've actually managed to get the measuring the magnitude of the acceleration data and the angular velocity. So we're doing the data analysis with this R script, and this is what then gets built into that the machine learning model. So what's next for this? Well, we're looking for the future to new sensors, adding micro SD cards, so we've got much more local storage on them. Very interesting development with sensors is high precision global navigation. This is high precision GPS. So GPS is quite all right, but it's not super accurate. But there's a whole new generation coming along of assisted GPS that is like to the centimeter or to the millimeter, really accurate precision tracking. There's these kind of sensors are apparently only just around the corner. We're looking at handling continuous network connectivity as well in sensor kit as well. We don't want to support only this kind of intermittent connectivity model, and we want to look at the edge computing, enhanced edge computing, so enhancing the software that's running on the phone and also on the chip, so that we can do a little bit more processing close to the point of data collection. And of course, we're going to have to do more data collection. So this is a few of the hard working days I've had to endure this winter. I think that was Austria on the left and Spain in the middle. And then, of course, after a hard day of coding, you need to hit the hot tub. So we had to do that. And this is Crystal Mountain in Washington State. That's Mount Rainier behind. Another hard working day. This is Kevin Ashley fooling around. He's actually a ski instructor. He's on our team. This was Austria. This was a very tough week. The cloud was down a few days. We didn't actually get as much sunshine that week, so we had to do more coding than skiing. Shock. And Copper Mountain in Colorado was early in the season, so no doubt we're going to have to do lots of that. I did suggest that we really needed to go to New Zealand in our summer. That seems completely reasonable to me, but somehow I think that was actually even a step too far for some of our people in the team. So, yeah. So that's it. Thank you very much.